Hello, everybody. Welcome back to Mankind in Training. It's nice to see you again. I have today another walkthrough. We're going through the Wolfram Alpha Quantum Computation Framework. I've had it now for a little over a week, and I'm extraordinarily impressed with it. There are some issues, I think, having to do with speed, and it might have to do with memory allocation, or I'm not entirely certain what the issue is with that, but most of the time it works splendidly, but other times not so much. So here is the Wolfram Mathematica. I've opened up a Wolfram notebook, and I've already done quite a bit of stuff. What you want to do though is install the packlet, the Wolfram Quantum packlet, and I'll put that there for now. And after you do that, it doesn't always work. So you need to find this in the documentation, the packlet uninstall, and then there's a bunch of direction in here, and then you force version install, and then after that, it seems to work just about every time. Anything that I'm trying to do. So with this framework, there are a series of things beginning with the first thing that you should probably know is there is quantum basis is the first thing we're going to work with here. I don't know why that's there. Okay. So let's say I have this quantum basis here, and I'm going to make it a Heisenberg. And what that did is create quantum basis. And it has one qubit, and it's two-dimensional. And convert this to the traditional form. It just gives you the associations, sparse array. So now I'm going to convert that back. Or no. That's very strange. It should have did that. Okay, so now the next thing on the line. Well, let's look at some more quantum basis, some of the named ones, and what they look like. So another quantum basis is the Dirac basis, and it looks like that. It is a Schrodinger, dimensional, one qubit, 4x4. And if I look at the traditional form there, this is what my Braunket notation looks like. So let's go. No, not that. Let's go not that. Go this. And let's just show you what a Pauli X like. We have this here. And there we are. Pauli X1 or minus Pauli X plus. And then you get the amplitudes. probability densities and the amplitudes. Let's bring the X back. So the next thing down the line is you take a quantum basis, and then quantum basis can have quantum state. So let me make Pauli X quantum state. And now I have a pure state Schrodinger vector, a two-dimensional, one-qubit pure state Schrodinger vector. Formulas. That. So now what if I go like this? C and D. And then there we go. Now let me show you what that looks like. Now I have a four-dimensional version of this quantum basis Pauli X, but it's a state now. It has states A, B, C, and D, and they each have their Pauli X variation of the minus and plus. So now let's see here. What else do I want to show you? So now just to show that, so quantum state X equals quantum state Pauli X, and that says that they are exactly the same operator. Now what else do I want to do? What else do you want to show? Okay, so oh yes. So very quickly, nextly along the line, we have a quantum state. So we have a quantum basis, we have quantum states, and now to do operations on the bases and states, you have quantum operators. So we have a quantum, just like in computational physics, all of the things are here, and this is just, I love it. I love it. I love it. I've been like glued to my laptop for the last week. The Wolfram has a course and study group and bunch of different the documentation's out of this world. There's so much. There's so much. It's very well documented. I am a fan. Stephen Wolfram. I am a fan. This is excellent. Anyway, so I'm going to use let's say a permutation. Permutation operator. Yeah. So now I have a permutation operator. Yes. And I want to do that operator on the quantum state. X. It doesn't want to do this. No, let's just give it that. No, doesn't like that either. Um, why is that doing that? There we go. Yeah, I wonder why that wasn't doing that. So I want to do a permutation operator on the computational basis. Six matrix form. There we go. And that's what the operator looks like in a matrix form on the computational basis state. So you have quantum operators. So we have named a bunch of named quantum operators, like magic operator, for instance. Magic. There we are. So this is a named operator called magic, and these are its associations with the various sparse arrays. View a series of sparse arrays. So next we have the quantum operators that you're doing on quantum states, quantum bases. The quantum basis, most basic here is mm, sometimes it doesn't do what you think it would do. There. That's what I was trying to do. Kind of. I was trying to show you that you could literally name the states, but or name the qubit names, but it was being difficult. It does not want to do this for me. No, it does not. Doesn't want to do it. So, nextly, quantum operators. That's where I'm on. Okay, so say I want this. I want the QFT operator. Sensor network. Does not want to do this. Give me the index graph. Doesn't want to do that either. Okay, so what if I did this? Do this? No, it doesn't want to do that either. Sometimes the things work how they are supposed to, and other times they do not. That's so very weird. So I already know that this works. So I wonder why it does it for these and not. That's very strange. See, I'll show you. I know that works because I've already done it. Right here. Ha, ha, that's why. I get it. I get it now. I get it. Ha, ha, just get ahead of myself. So, quantum operators. Quantum circuit operators. Now, getting somewhere. The quantum circuits are themselves being run on the quantum computers. This should work now. I'm pretty positive. There we go. There. And this will show you the exact tensor network and the directionality, the indices, names, weights if they have them. Yes, 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 yes. And this here, yes. The inverse Fourier. I just actually before I lose this. Before we lose this, show you that and diagram. Show me diagram. All right. This is the inverse Fourier, and this is a diagram of what it does. And there are two swap gates here. You have a Hadamard and then a controlled with the pi to the 1/2, and then another Hadamard gate. This is a quantum circuits operator, inverse Fourier. So if demonstrate, whoa, not 45, not 45. All right, so what I did just now was this was only on 2 gates, but I made it so it does it on 4 qubit operations. So now let's me go. I won't do any of that yet. Quick. So what if I do this here? So I do not specify. Yeah, it doesn't work either. Oh, here we go. I think maybe this will work. Sorry, I'm still figuring all this out myself. Yes. Mm. Oh, yep, 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 yep. Yep, 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 I see it. This is still not quite doing what I want. Okay, so what if I was to get rid of these and get rid of these back to here so I can show you what Grover looks like, the phase diffusion version of it. It's odd. That's very weird. Whoa. There we go. That's what I was looking for. Yeah, what's going on with that? Anyway, this is what a Grover diffusion circuit operator looks like. It's got a bunch of Hadamards all down, and then you have a bunch of X gates. You have one Z. You have a bunch of NOT gates. The Z flips the X, and then the H's take it back. The H is your Hadamard operator. So I got no. Your Hadamard operator. Yeah, whatever, I will find it. Okay, so quantum. I don't know why it does that. Quantum operator H matrix form. There we go. And that's what the Hadamard does. So I want to go. What was I doing? Um. Oh yeah, yeah. Type. Hmm. There we go. Kind of. Ah, I think that's more what I want. There we are. That's not quite what I was looking for. Um, and why is it not what I'm No. Okay, so it does want that. No, it's still not what I'm looking for. It's not even doing the measure anymore. Huh, that's weird. Anyway, so let's go with this. So just for the learning purposes, I'm going to have a quantum state. Random here. And I'm block plot. There we go. So this is the block sphere. And this is one of a few ways that we can denote the amplitude and charge of your qubit. In range 0 to 1, positive, negative, left, right. You can also incorporate, so say I had got theta here and negative theta down here, or you could have a e to the I pi and then negative e to the I pi. You can really use the block sphere in all sorts of different ways. Any opposite thing that you can think of to counter onto it. So now I have this particular state. So I want to do a quantum measurement operator on this state here. I'm going to do a quantum measurement for the first time here. Show you it looks like so, sampling from my circuit. So now I get a quantum measure. I'm measuring one of the states from the circuit randomly. Uniform formation. So I would like here the probability. That's weird. Okay, so let's try this. Composition. That really should have worked. Okay. Why is that? No, maybe I don't need to designate. That's weird. Okay, so maybe this is how you need to do it. Anyway, that is what I was looking for. You get your measure, and it gives you your probability densities for the measurement. Which doing the operations, but it's not measuring them. It's creating my states, but it is not returning me my measurement states. Anyway, and you can also turn these into Qiskit objects and measure them with IBM as well. You don't have to use the Wolfram Quantum Computation Network, but so like this is a series of time measurements here from the actual server. When I run psi, when I run psi1, eta and theta's angle through I1. So let's go to your settings. Ah, yes. So all right. We do that again. We wrapped it. Wrapped it. Okay. E1 equals. I get just get a random graph here, so I get to creating a quantum circuit operator. Did I need? Let me just look right quick. Do we need? Yes, it needs to be. I did indeed need to do this. All right, I suppose we're probably running out of time. I don't realize how long I'm taking until I take too long. So I should probably get a move on. All right, so this is a random graph operator that I made that samples from the circuit at random in a tensor order at random. And then I'm creating that same random graph and using its order and its tensor indices, all of it. I'm using all of it to create a quantum circuit operator to randomly sample, and then you can, from the random samples, build probability amplitudes. So this is a quantum circuit operator made with the conditions of this graph. Okay, what else? What else? So we got to circuits, we got to measurements. Now, what else was there to show? Oh, the fact that you can wrap exponentials. Oh, that's really the functionality. We want to show some of that here. So right here, this is a rotation on the x qubit. On the third, let's see here. Get a good one. You guys can really see what's going on. I can fiddle with stuff and show you. Okay, so let's make this my new end piece. And all right, so let's go for E 1, 3 XX onto RX, and then a measurement on 1 and 2. This is a quantum circuit operator, a custom quantum circuit operator where I'm literally picking exactly where everything goes, directing. I have a quantum Fourier transform on the 4th of the 1st. I have Y and Z. I have two X's, my XX on the 2nd register, and a rotational X operator. And then I have my measurement operator on the 1st and 2nd qubits. Let's go. There should be before that here. Should be a yes. Yeah, that should be fine. That should be fine. Something like that. Okay, so right there we go. X. It's a good example of how to actually set things up when you're building from the ground. What was another good example? Showed. Oh, this is. So you can really do pretty much anything you want. So, yeah. Yeah, it's not even gonna play with it. Not. All right. You can wrap anything in an exponential form like so. You can also change. Yeah. There. Um, there. What's another thing I want to do right quick? Oh, just to show that you can. There we go. You can literally do mathematical operations on the state. And you can write, oh, it's another good example of, let's turn a set of notation into, I liked how they did that the one time too. That, um, oh, so I have this here. This is my output for this magic operator here. So what if I want to do negative I over root n tau theta negative alpha I 2 3 theta 4 plus I goes I over I 2. All right, anyway. Um see if it will let me do that. Kind of. Kind of let me do it. Anyway, so here's another decent example. The tensor network of the Fourier transform, where the phase shifts and things happen. It's circuit that you can run random unitary operator. Oh, yeah, it's another thing I wanted to show. Quantum up. XYZ. Diagram. YZ, just like so. And that's how it recognizes it. There we go. That's the order XYZ, ZYX, and then left to right like that. I was about to show you something though. So where I measured with the Wolfram network actually, or I do have that example here. Oh, I like yes. So I here create a quantum state, a Dirac state well, it's a direct basis, and I'm specifying the quantum state here, and let's do that. So I'm naming alpha, beta, gamma, and the imaginary kets E0, E1, E2, E3. Yeah, this probably isn't going to give me what I want. Oh, kind of. It kind of gave me what I wanted. Anyway, it's real quick, real quick. I'm almost done. Almost done. Swear. The depolarizing quantum channel. Yeah, I should have said something about that. Oh, swapping. Okay, so 1 through 4. I'm swapping on 1, 4, 2, and 3. Swapping on 2 and 3. The depolarizing quantum channel. Oh, I was going to show you a quantum partial trace too. I'll have to do that in the next one. The quantum partial trace. So, where was I? Right here. Here's a good example of this a circuit that I built up from like nothing. So I started out, and just like so, quantum circuit operator bell slash times quantum circuit operator Fourier on 5 slash times quantum circuit operator, and I got a Grover phase diffusion at the end on 5 qubits as well. So this is how this starts off. You have a Hadamard gate, and then a controlled NOT gate, and then another Hadamard, and that's the magic, or the bell. It's a bell right here. And then next came my quantum Fourier transform on 5, and that looks like maybe actually this is looking like this is part of, perhaps my bell actually stops after the NOT gate. And because I do remember there being a Hadamard at the beginning and the end of a Fourier. So there's a Hadamard, your series of controlled pi to the sequence gates, Hadamard, pi to the sequence gates, dual Hadamard, X flip, pi to the half, Hadamard, 2 swap on 2 and 4, and then a swap on from 5 and 1 to begin your phase diffusion. And that will come in on 1 and 5, be flipped to 2 and 4. The 2 and 4 will have to be pulled. The Z rotation, you get it back at the X's, and then your Hadamards changes them all back to their origins. So, this has been lovely. Thank you everybody for watching. I am going to exit out for now. I will be back though with more. This is the most impressive thing that I've downloaded in some time. It might be the most impressive piece of software that I've actually gotten to work with at all, really. I'm very, very impressed. So thank you everybody for watching. There will be more quantum computing. There will be more just programming in general. There will be more math in general. There will be more science in general. I am starting a foundation, nonprofit organization for the study, fundamental physics, for the advancement of quantum computation technology. I have tons and tons and tons of ideas for experimental physics, things that I'm almost certain will yield amazing results. I just need the funding. So onward and yonward, and I will see you in the next installment. Thank you for coming, and I will see you again. If you like, subscribe. Good day.